All right, so today I want to talk with you about superposition. And so maybe briefly we can just do a little bit of review of some of the things that we've already learned. So we do know now about how to relate the frequency of a wave to its speed and its wavelength. So maybe I should just try a couple of examples just to refresh our memory here. We also know that the period is inversely related to the frequency. So going to the dot cam here, let's just kind of practice a couple examples. If I was given that the speed of a wave was, for example, 340 meters per second, and I was given that the wavelength, the distance between the peaks, right? And if it's a longitudinal wave, this could be thought of as the place where the pressure is higher or lower, right? And so if you remember, this baseline here is somewhere around 10 to the 5 pascals, and it's only plus or minus a fraction of a percent, so the amplitudes are usually very small. This would be our length of our wave. So for example, if we had a length that was 2 meters, we could say, well, what frequency is this? And remember that frequency is ultimately going to be related to the pitch that we actually hear. This would be V divided by lambda. And so if I did 340 meters per second divided by 2 meters, I can do that one in my head, I think. No, this one is, let's see, so I think it's, 34 divided by 2 is 17, so it'll be 170 hertz. And actually, while we're at it here, I've got a tone generator open, and I'd like to start making these numbers become something that's real for us. And so if you just type in on Google, if you type in tone generator, the very first link that comes up is this, I don't know, SZ Zinalski, I don't know, but anyway, it's a free online tone generator. I'm sure anyone will work, but here you can hear the sound. So if I play this, dang, I was hoping that we would be able to hear this together. Let's see, is there any way to do this? No, unfortunately not. For some reason, the sound doesn't work when I try to play it through the apps. Bummer. Okay, well, I will let you play this here. And if you just type in online tone generator, you'll find this and you can play the notes. And it should sound something like this. Ooh. And then when we bring it down lower, you should hear boo, and then boo. I'm just kind of trying to do it by sound since it's not working on this right now. So anyway, this is the way that we can hear these sounds. And 170 hertz is going to be a sort of a low tone sound, but since it's between 20 and 20 hertz and 20 kilohertz, we should be able to hear this sound. Another way we can review here is we can ask, well, in time, we can also think about, if my ear was some distance away from this thing, and I was also feeling this pressure changing, going from high to low, something like this, then I might ask, well, how much time has gone by between one high pressure and the next high pressure? And really what this question is asking is, well, what is the period of this oscillation? So maybe you know that you can take the frequency and just take 1 over that. So for example, if I did 1 over 170 hertz, which is inverse seconds, I've got to use a calculator here at this point because I don't know how to do that in my head. If I take out my calculator, I find that I can do 1 divided by 170, and I get this number here, 0.005, and I'll just say 0.59, just as an approximation. Now this is in seconds because we have a 1 over seconds, which gives me seconds. But if you notice, this number is a little bit inconvenient, so I'm going to change this instead to milliseconds. If I want to change to milliseconds, I can just slide the decimal place over by 3, and I get 5.9 milliseconds. So this would be the period in milliseconds. And I'd like for you to be comfortable with changing back and forth between milli and kilo and things like that. Mega, micro. Be able to change between these different units. So that means that every 5.9 milliseconds, there's a new high pressure wave, or new high pressure moment that's coming. So that would be exactly if I took 1 second, right, and I divided it into 170, this is just representative here, if I divided that 1 second into 170 little divisions, then one of those little divisions here would be a period, okay? Would be that 5.9 milliseconds. Anyway, so that's our review, and now we'll continue on with some new material. So the concept here is that my slogan that I'm going to kind of beat the drum over many times during the course of this lecture here is that superposition means that waves just add. And in a moment we'll actually get to this formula about beats, and you'll be using this in some of the homework. So when waves cross paths, they just add up with each other. So in other words, if I had a wave coming from the left and a wave coming from the right, these are different moments in time, you'd see that they would add up with each other. And so when they're actually coinciding, you get a kind of a wave or a disturbance that is twice as big as any one of them, and then you see them moving through each other. If one is up and one is down, in the moment that they actually meet with each other, then they actually cancel each other out. And then you see the sort of the down displaced disturbance or so. It's moving through. You can see it moving through here, and the up disturbance is moving through to the right. Similarly, if I had two pulses, one is sort of a square shape and the other one is kind of a smoother shape, notice how they add up with each other. I've got the square box and I've got this sort of other thing added up on top of it. So those are other ways that you can think about waves adding with each other. The box then moves through unharmed, and so does the smooth one as well. But while they were on top of each other, they added with each other. So in chapter 3 of your book, you can also see the concept of wave reflection, and you've seen this also in some of our demonstration and activities in class, that if you have a fixed end and you give it a little transverse pulse, then it'll be an up wave on the way there and it'll be a down wave on the way back. And that wave is traveling at the same speed so long as the tension is the same in the string. And so in this way you can see a loose reflection. You can see a wave reflection. And also, if the wave has a loose end, you'll also notice that it pretty much does the same thing, except for the transverse wave that goes to the right it's on the same side as it comes back. So what do I mean when I say waves just add? Well, the technical term for this is called interference. And you might think of interference like maybe in a sports sense or something like that, as meaning that it's doing something negative or something like that. And that's indeed one interpretation of this. But also just the simple addition of waves is what we call as interference for our purposes. So, for example, if you see the wave that I have above here that has some particular amplitude and frequency, and this other wave that looks like pretty much the same amplitude but a higher frequency, if we take every moment along these, so for example, take this moment here and this moment here, they're going to add with each other to make something that's bigger. Whereas, for example, if I take this moment right here that's up and this moment right here which is down and I add them, you get this one that's very close to 0 here. So in other words, if I take this shape and I add them to each other, I get this fairly complex looking waveform. So this is the meaning that I'm saying about waves are just adding with each other. So we can have a constructive interference case. Notice that the peak of this one coincides with the peak of this one. The bottom of this one corresponds with the bottom of this one. If you add these two together, you get something that looks pretty much like either one of them, but it's twice as big in amplitude and the frequency remains the same. Similarly, if I just shifted this over by half of a wavelength, you see how the bottom one here is shifted over by 180 degrees or half of a wavelength. You notice that a peak here corresponds with a trough here, and a trough here corresponds with a peak here. If I add these two together, I get something that's almost exactly 0. This is called destructive interference. So the two key terms here are constructive and destructive interference. So you can imagine that if you have two waves constructively interfere with each other, the sound that will occur from it is going to be louder. And in the case for the In the case for the destructive interference, the sound will become quieter. So here's our concept here, is beats. This is an example of temporal interference. When I have two waves that are very close to each other in frequency, but not quite, then we notice that they sort of get out of sync with each other. And the perfect example that I think works for me is have you ever been at a traffic light and you notice that you maybe have your left blinker on, and the person in front of you also has their left blinker on. And of course, this is California, so maybe not everybody has their blinkers on. But if you notice the situation, sometimes the blinkers are like almost the same frequency. In other words, they're flashing at the same time. But if you watch long enough, then you might notice that they get out of sync with each other, and then they get back into sync with each other, and so on. Well, this is pretty much the concept of beats here, is that you can notice that at the beginning they're in sync with each other, but the orange wave here is 105 hertz, and the blue is 100 hertz. And so you're noticing that after a few cycles, the orange one is now at an up, whereas the blue one is now at a down. This corresponds to a destructive interference, which you can see here on the right. And so there's going through a destructive interference, and then if we watch it long enough, it goes back to a constructive interference again and again and again. And so the difference between these two waves is 5 hertz in frequency. And so you can actually then immediately read off that the frequency of the beat that you're going to hear, in other words, how many times per second does it get louder to soft back to loud again, it's going to be 5 times per second. And actually, I just realized something, that I had the this earphone jack plugged in, which is the reason why it wasn't making sound earlier. So I'm going to go ahead and try this. So for example, if I have something that's at 440 hertz, and I play this sound, and if I do, I'm going to open up another instance of this and also play 440 hertz, but now I'm going to move it up by 1 hertz. Now 2 hertz. Can you hear 2 times per second? 3 times per second. So now it's 443 compared with, let's see if I can kind of put these two next to each other here. I don't know if I can get them to display both at the same time. Yeah, there we go. So here's the two, right? So these two are interacting with each other now. I've got this one at 440 and this one at 443. So you can play with this, open up 2 instances of the tone generator, and you notice that when one is 450 and the other one is 440, the beat that you hear is that da-da-da-da-da-da thing is happening 10 times per second. And then as I get the 2 tones closer to each other, once they're actually coinciding, you don't hear any beats anymore. They're perfectly in tune with each other, and their interference is completely constructive. Okay, so that's our demonstration there. Similarly, you can also see that I've put on here a calculation for frequency is 1 over the period. We can also just write that as capital T here. The period is 1 over the frequency. So I can take this 5 hertz, take 1 over 5, and that's 0.2. So in other words, the timing between from going loud to soft back to loud again is 0.2 seconds. So that's the concept of beats, which is a temporal interference. Here's another picture of this here. This is a situation where you have a 100 hertz signal and a 120 hertz signal. And now, if I look at it in time, you can actually see visually here that they're in sync, and over here they're exactly out of sync, which is destructive interference. And then after a few tens of milliseconds later, they are actually in sync again, and then out of sync again, right? And you can see the result here in terms of this wave is getting, remember that the higher the amplitude, that means that it sounds louder. So it sounds loud, soft, soft. And it does this 20 times per second. And that's because these two frequencies are exactly 20 hertz away from each other. And so The period then is basically 50 milliseconds or 0.05 seconds. So actually, just for fun, let's try to do that, exactly what that is. So there's 100 hertz tone. Turn the volume, it's a little quiet. And then here's another 120 hertz tone here. Close enough. Interesting. What you're hearing is 20, that's 20 like pulses or whatever, is 20 getting louder and softer per second. So that's that brrr. And in fact, if you make that sound with your tongue, that like brrr kind of sound, actually you are making your tongue go up and down like 20 or 30 times per second, which is kind of a neat thing to think about. So anyway, there's another idea about beats. This is just one more picture of it. It's pretty much the same thing, but I just thought I'd include this in here just to provide some different perspective. This is of that 100 hertz and 105 hertz, and you can see that the places where it's constructive and destructive interference, constructive and destructive. So anyway, in summary, the beat frequency that you hear is basically how many times does it become loud and then soft, and basically per second. And this tells you that it's 5 times per second. So that equates to there's 5 of these bigger lobes here per second. And yeah, so you can basically say that the period then is going to be 0.2 seconds for this situation. So, all right. We also have labeled here what this is like when it actually gets to your auditory canal and you're actually hearing these sounds, is that if you have one frequency and the other frequency, in the moment that they both arrive, and if it's constructive, then you'll hear a louder sound. If it's destructive, you'll hear a softer sound. Okay, so here's a question for us here. Which pair of tones would be most likely to have a slow and very distinct beats? And this might be a relevant question for if you were trying to tune a piano, for example, as is shown here in the image on the right. So I'll let you stop for a moment and try to think which pair of tones of these listed here would have a slow and distinct beat. Okay, so we're back, and you might notice that 10 and 40 hertz and 100 and 140 hertz will definitely give you beats, but these are going to be, the difference between 40 and 10 is 30, and the difference between 140 and 100 is 40. That means 40 times per second, so that's going to be a very fast beat. It'll be like that, whereas the difference between 100 and 102 hertz is going to be only 2 hertz is the difference. So that's going to be like a wah, 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 like that. So if you guessed C, then you were correct. So hopefully now you're beginning to understand what I mean when I say that waves just add. Now, that's temporal interference. So everything about beats is talking about interfering in time. But there's another way that waves can interfere, which is called spatial interference patterns. So here's kind of a cool image here of some boats that are actually just at a dock. And it's actually, this is kind of an image just from Google, where you can actually see these different rings that are emanating maybe from this boat, maybe from this boat, and maybe from this boat. Maybe the boats are going up and down a little bit. There's some displacement, and it's creating these really nice looking ripples. But if you look closely, you'll actually see some places where the ripples overlap. And so, for example, you can imagine that where a crest meets a crest, that it would be a larger displacement of the water, whereas if a crest meets a trough, they're going to destructively interfere with each other. So this is a kind of spatial interference pattern. One way to visualize this is if you had 2 speaker sources. For example, one is over this arrow and one is at this arrow, and if they're equal distant away from each other, then a peak is going to meet with a peak, and it will be always a constructive interference at this place. However, if you change the distance between these 2 sources a little bit, so that a peak here meets with a trough here, they'll destructively interfere with each other, and at that place it will appear very quiet. audio engineers have to think about all this, and so they might create these arrays here, or multiple different speakers in order to minimize the amount of dead space. And so you can actually see here, this is a fairly kind of advanced example of the engineering that's required to minimize the destructive interference, so that everybody in the home theater or something would be able to hear the sound without it sounding really quiet or unpleasant kind of change in the quality. So if we just think about a case where we have two speakers, so notice these two green dots here will be our sources here. Each of them has a series of rings around it. And so these correspond to areas of maximum pressure and minimum pressure. And so if you notice here, you could think about the thinner lines as being like the trough, and the thicker lines as being the peak. And so when a trough meets a trough, like so when the trough from the source 1 meets the trough here from the source number 2, right, then that's actually what is called constructive interference. Similarly, when a peak meets a peak, so that when thick lines intersect, one is from source 1, the other one is from source 2, when they meet, it's constructive interference. So the condition here is that everywhere along this sort of the red dots lines here is going to be a loud place. Everywhere along the blue dots here is going to be a quiet place, where we have a peak from a high pressure place from source 1 is meeting a low pressure place from source 2. You're going to get a destructive interference. So that means that anybody standing along this line here is going to hear it as soft. And we will actually do an outdoor demonstration in our class where you will get to experience the constructive and destructive interference. So this is our image again. We might refer back to this. So basically, peak meets a peak, constructive. Peak meets a trough, destructive. So here's kind of a nice little animation that will sort of help us to think through this situation here. So how many wavelengths is this point A away from S1, source number 1? And how many wavelengths is it away from source number 2? So we can notice here, if we just count, this will be one wavelength, is from the source to this first line here, second line, third line, fourth line, fifth line. So I would say that A is 5 wavelengths away from S1. Now let's count from S2. 1, 2, 3, 4, 5, 6. So it looks like it's 6 wavelengths away from S2 and 5 wavelengths away from S1. So this is an animation here of what we just basically went through, that there's 1, 2, 3, 4, 5 wavelengths if you count those. Now how about from S2? If we count those, we can say that the distance from S2 to A is 1, 2, 3, 4, 5, 6. So it's 6 wavelengths. So do you think that at point A you're going to hear it as being loud or as being as very soft? Well, the difference in path between those two is just 1 full wavelength. So we get a crest meeting a crest, or in other words, that's called constructive interference. So how about this point? Is this constructive or destructive interference? You can count here that the distance is 4 wavelengths. Can you do that? 1, 2, 3, 4. And how about the distance from S2 to point B? Can you confirm that it's 6 wavelengths? 1, 2, 3, 4, 5, 6. Yep. So is that going to be constructive or destructive? What do you think? I would say that looks like it's going to be constructive interference because it's an integer number of wavelengths, which means that you get a crest meeting a crest. So if you have a difference in path length between, let's say, 6 wavelengths and 7 wavelengths, a crest meets a crest for constructive interference. If you have a difference in path length between 6 wavelengths and 8 wavelengths, also crest meets a crest, constructive interference. But what about, and what about if you have 6.5 and 7.5 wavelengths difference? Well, here it's a trough meeting a trough. It will also be constructive interference. But let's take a look at this. What if you were 3.5 wavelengths away, where for one and 4 wavelengths for the other? Here, a crest of the red one is meeting a trough of the blue one. This is going to be destructive interference. What about this one? Here we have 6 wavelengths and 4.5 wavelengths. What do you think? This is going to be destructive interference. We have 1.5 wavelengths away, which is, you could say that it's not an integer number of wavelengths, but it's a half integer number of wavelengths away. So that would be a way to think about it. That's our condition for constructive versus destructive. So notice how in each of these examples that I'm introducing to you, like I'm trying to do it in a way that gets you to intuitively grasp what's going on. We haven't actually had a formula yet, but I will provide you with a kind of a summary toward the end of this. So let's try an example here. So please pause here and try to solve this either alone or with the partner if you're watching this video with someone. Okay, so to solve this here, we should really draw some kind of picture. The way that we can think about this here is I'm going to draw the picture as I'm watching this here. Let's see if I can kind of multitask here. I'm going to open this up and I'm going to have this thing open on the other screen so I can do that at the same time. Okay, good. So we got the 2 point sources and they're 3 meters apart. So I'm going to have one point source and another point source. And one person stands in a place that's 8 meters away from one and 6 meters away from the other. So if this one, let's say, is the 8 meters away and this one is a 6 meters away, right? So 8 meters, 6 meters, then this is going to be 3 meters. Of course, it's not perfect, my drawing, but you get the idea. This one's longer, this one's shorter, this one's the shortest. The wavelength is 1 meter. So I could actually draw these wavelengths. I could draw 1, 2, 3, 4, 5, 6, 7, 8. And the other one is 6. So 1, 2, 3, 4, 5, 6. But the point is that whatever's happening over here, for example, let's say that there's a crest over here, then because it's an integer number of wavelengths, then it will also be a crest over here. So it looks like I'm going to have a crest meeting a crest. So that's how we can solve the problem through drawing a picture. And let's bring this back here. And so the situation is basically this situation here, which has been discussed, and the wavelength is 1 meter, but the path length difference is 2 meters. So that's 2 full wavelengths of path difference. So it looks like it's a constructive interference. Okay. Now let's look at a separate example here. 2 point sources are 1 meter apart, and they're generating periodic waves in phase. That means that they're moving together. And a person stands in a place that's 12 meters from one source and 9 meters from the other source. So notice how actually the 1 meter apart is good for the drawing the picture, but actually it's not an important part of actually solving the problem. The meat of it is in we have to figure out what the difference is in path lengths compared with the wavelength. So let's make a physical sketch and a sketch of the physical situation, and then determine whether it's constructive or destructive. So I'm going to again go back to the image here, and I'm just going to draw these 2 speakers as being 1 meter apart from each other. And in one case, I could draw it over here, for example. This could be my 9 meters away, and this one could be my 12 meters away, something like this. So this could be our setup for the thing. And if you notice here, the difference in path length, I could say delta path length, something like this, difference in path length, is equal to 3 meters. And so if you notice here, the wavelength is equal to 2 meters, right? So in other words, that delta D, I could call that the difference in path length here, is equal to 3 meters, which is actually 3 halves of a wavelength. That means that at one point, it's going to be pointed, let's say, a crest here, whereas it's going to be a trough here. I can just, just kind of thinking about this idea like something like this. So if it's a peak here, whatever this one is has more, right? Then it's going to be a trough here. So in other words, there's going to be a destructive interference because of the fact that these are not integer number of wavelengths difference in path length, it's a half integer. So the point is that if you see ever a half integer difference, that's a signal to you that it's actually a destructive interference situation. So again, let's take a look at the example here. We have 4.5 wavelengths on one path, and we have 6 wavelengths on the other. So it's it's this situation here. The difference in path length is 3 meters, but if the wavelength is 2 meters, then that's going to be 1 wavelength plus a half wavelength. And so that plus a half wavelength results in destructive interference where a crest meets a trough. So here is the summary of how you can solve these kinds of problems. I strongly recommend writing something like this down in your crib sheet or some piece of paper that you're going to be using while you're solving problems. Is that when the difference in paths is an integer wavelength, in other words, if the difference in distances is the same, or if it's 1 wavelength or 2 wavelengths or 3 wavelengths and so on, you'll always get a constructive interference at that location. However, if the difference in path lengths is like half of a wavelength, or 3 halves, or 5 halves, or 7 halves, or 9 halves, etc., but just not an integer number, then that'll be a condition for destructive interference. So let's practice. Oops, I just showed you the answer. But if 2 speakers are playing the exact same pure tone at 172 hertz, and you're 1 meter away from one, 2 meters away from the other, what will you hear? Well, I can guarantee you there's no way that you can do this without picking up a piece of paper and trying it out. So I want to encourage you to give it a try and see if you can make some sense of this one. Okay, so let's go to the dot cam here, and I gotta actually be looking at this at the same time as I talk to you here, so all right. So we have 2 speakers that are playing the same tone. Now, you might be thinking, well, wait a second, I don't really remember, I thought we had to have a wavelength here, but we were given a frequency, right? 172 hertz was our frequency, right? But if you remember from our review from the beginning, that's a fairly straightforward exercise to go between wavelength and frequency, or frequency to wavelength. And if you actually remember, the exact example that we did at the very beginning here was actually something where we had a wavelength of 2 meters and ended up with a wavelength of 2 meters ended up in a frequency of about 170 hertz. So now, if you're not told the speed of sound, you can guess. And 344 is our sort of magic number. That's something that you can know is sort of the speed of sound at room temperature. Speed of sound at room temperature. Okay? And remember that just increasing the temperature a little bit is going to make it go a little bit faster, and making it a little cooler is going to make it go a little bit cooler, a little bit slower, but okay, it's basically, that's the idea. And if we divide this by 172 hertz, or 1 over seconds, the 1 over seconds cancels out, and we're left with 2 meters is our wavelength. Good. So now we have the wavelength. And now the other part that we have here is that we have 2 speakers, and I'll just make it over here. One is 2 meters away, one is 1 meter away. So 1 meters, 2 meters, and here we are. I'm going to draw a little star right there. And we have our difference in distances here. So in other words, our delta D, our difference in distances, is 2 meters minus 1 meter. So that's 1 meter. And we can see that that's equal to basically half of a wavelength, right? Because our wavelength is equal to 2 meters, but we only got up to half of that, right? 1 meter. So that's how we can solve that kind of problem, and that's how we know that this is destructive interference. So, by the way, a pure tone, this is a sinusoidal waveform, so we don't have to have any complex waveform. So we have destructive interference here. All right, this one's a little bit of a challenge question. I'm going to leave it up there, and I'm going to not explain this one right now, but if you're curious and you want to find out, please bring it up in our meeting, and we'll discuss it. Okay. Thank you very much, and I think that's everything. That was just a kind of review one, and I think that's all the slides for right now. So thank you, and hope you have a good day.